Let's do a quick review of how a graph of a sine translates around and how various coefficients and the translations affect its shape. So we're going to do this in anticipation of a modeling with periodic functions and sine graphs in our next example. So here we have a graph of a typical sine function, y equals sine x. Right, so a typical sine function, as you recall, has an amplitude of 1, which means it's attains its highest value at y equals 1, and it's periodic at the other end. The lowest value will be at a -1, and it comes back up and goes to the positive 1 again. It has a period of 2 pi, or 6.28 roughly. That means it will complete one full cycle in 6.28, and then it repeats again. And a typical one would have no phase shift, so it would start at 0, 0, and it will continue. Well, when we say start, we usually look at this as being our primary cycle. If we were going to graph a sine function based on the coordinates of a unit circle, we would start at 0, 0 and go around. Now, as we adjust the coefficients, so what we have here, a is 1, right? So typical full complete sine graph would have a coefficient in front of a sine. In this case, that's 1. It would have a argument inside of a sine, which would be b times x minus c. And the b would dictate the period of the function and also the frequency. Those are inverses of each other, if you recall. And the c here would dictate the phase shift, right? So move the graph left and right. And finally, the d would give the graph a vertical shift. So we'd take the entire graph and move it up. So if I just kind of go and play around with this, with these sliders, we'll see how it affects it. So if the sine function that I have, just again a basic sine function, a is 1, right? So 1 times sine x is just sine x. B is 1, there's no coefficient in front of x. C is 0, right? There's nothing added or subtracted to the x. And D is 0, so nothing's been added to the function. So it's sitting where it would have typically have been. Now, if I increase the a here, so as a increases, notice the amplitude increases. So currently that a is 1.6. The highest value here goes about 1.6. Notice the period has not changed. It still goes through the same points here. Right now, if I go back, let me put this back at 1, and this time change just b. So notice as b increases, in this case the period keeps getting smaller. I get a larger frequency. That means I get more waves, but that as a result it takes some less time to complete, right? So here I have a b, and let's say I'll change my b to be 2. So 1.94, and here's 2. Notice what happens here is within the period that the purple graph had, was a typical sine of x. Now I happen to have 2 cycles, right? So the frequency is doubled. I get twice as many waves within the same period that the sine of x has, but the new function has a period half as long, right? So it takes half as long for it to complete one full cycle. That's the effect of the coefficient in front of x, right? So let me move this back to what we had before, which was 1. Apologize, a little difficult to move it back. So okay, so let me move it back to 1. Oops. And then let's see what C does, right? So C will take my graph and moves it left and right, depending on its value. And then, so if I move the C to be 1, notice I have a phase shift of 1. My graph now has been moved to the right one. Okay, so we move this back to where it was, which was 0. 0. Yep, there we go. Now let's look at the effect of D. Right, so in this case, D, notice, moves the graph up and down. Now my D here is a positive D allowed in the slider. So as D goes up, the graph goes up. So in this case, if I go and make the D, let's say 1.1, this graph has moved up 1.1. Okay, so just a quick reminder of how these numbers affect our function, as we are going to try to take data points and fit the best sine graph we can fit through it.